the introduction on our project in instrumentation and control in a air compressor, test rig, and mini plant. The air compressor, test rig, and mini plant is used to measure the volumetric efficiency of a certain type of compressor, whether single stage or double stage. The project of the researcher is to improve necessary parts and elements found in the system, such that it will improve the way how students of mechanical engineering can use the system with ease. Control variable and manipulated variable can be found in the system and is indicated within this audio-visual presentation. On our project, instead of using LM35, the group will use DS18B20 as a temperature sensor, which the details will be explained later. The air compressor, test rig, and mini plant has some components which are broken. Such problems are encountered in the used temperature sensor. The air compressor, test rig, and mini plant has some components which are broken. Such problems are encountered in the used temperature sensor, which is LM35. The temperature sensor has the very low accuracy in determining the current temperature while on the operation. Also, one part in the system has a broken LM35. So, the researcher will try to replace and fix the current temperature sensor with a more accurate and easy to use temperature sensor, which is DS18B20. Also, a partial requirement for the manipulated variable, the researcher will install a circuit which will affect the speed of the motor of an AC pump. The next presenter will explain the project.
Now I will show to you the places or the various points where the temperature sensors are placed. Now, this is T1 before the heat exchanger system. This is T2 before the heat exchanger. This is T3 after the heat exchanger before going back to the cooling tower. And this is T4 after the heat exchanger system. The previous temperature sensors used are LM35. The researchers have replaced it with a new temperature sensor, a smart temperature sensor called DS18B20. DS18B20 is a digital temperature which measures up to negative 15 degrees Celsius to 85 degrees Celsius.
I will discuss to you the instrumentation system. The purpose of this project is to install a new set of temperature sensors which are more accurate than the previous used sensor. The researcher will be installing a temperature sensor, DS18B20, which will be installed into various points in heat exchanger. Currently, there are still two LM35 temperature sensors which are installed inside the tube in water intercooler. The temperature sensors are located on the following various points in the heat exchanger system. Temperature 1 before heat exchanger system, which is DS18B20. Then temperature 2, which is LM35 before the water cooler. Then temperature 3 after the water intercooler. And temperature 4 after the heat exchanger system. We will be changing LM35 to DS18B20 temperature sensor because of its advantages. One is to measure temperature from negative 55 degrees Celsius to 125 degrees Celsius. and it has an accuracy of 0.5 degrees Celsius from negative 10 degrees Celsius to positive 85 degrees Celsius. And third, it is also digital, so it is easier to calibrate. All you need to do is to download Dallas one wire and put it to to your Arduino for calibration.
I am to explain the manipulated variable and control system. The manipulated variable in the project of the researcher is the flow rate of water coming from the cooling tower. The water will flow through the heat exchanger system, which will serve its purpose of cooling air before going to the accumulator tank. The control system that the researchers will be using is a quadrat unit and combined with its circuit. The circuit for our quadrat is, as you can see here, the AC pump is connected to the circuit that is created for the quadrat. In this circuit, the potentiometer is used to variate the voltage that the pump will receive. The quadrat unit, which is coupled to a servo motor to control the potentiometer, in which then controlling voltage in the AC pump to manipulate its speed to control the flow rate of water from the cooling tower. In order for the researchers to monitor the flow rate of the water coming from the cooling tower, there is a provided water flow rate in terms of liter per minute. To control the flow rate of the water, the researchers have set a set point and limits in order so that the servo will turn 180 degrees to turn the motor on or turn to 0 degrees to turn the motor off. Quadracs are a special type of thyristor which combines a diac and a triac in a single package. Diacs are bidirectional diodes that switch AC voltage and trigger triacs or silicon control rectifiers. Quadracs are used in lightning control, speed control, and temperature modulation control applications. They carry performance specifications such as peak repetitive of voltage, peak repetitive reverse voltage, root mean square, on-state current, and temperature junction. Servo motor. This here is the servo motor used by the researchers. It is mounted to the quadrat already. The mounting is possibly made by a coupled servo motor horn that is screwed to a plastic knob. A servo motor is a closed-loop servo mechanism that uses position feedback to control its motion and final position. The input to its control is some signal, either analog or digital, representing the position commanded for the output shaft. The motor is paired with some type of encoder to provide position and speed feedback. In the simplest case, only the position is measured. The measured position of the output is compared to the command position. The external input to the controller. If the output position differs from that required, an error signal is generated which then causes the motor to rotate to either direction as needed to bring the output shaft to the appropriate position. As the positions approach, the error signal reduces to 0 and the motor stops. The very simplest servo motor used position only sensing via potentiometer and bang-bang control of their motor. The motor always rotates at full speed or is stopped. This type of servo motor is not widely used in industrial motion control, but it forms the basis of the simple and cheap servos used for radio control models.
Now we will discuss and show to you the codes used in our project. This is the first code that we use in order to measure the temperature at different various points at the air compressor test rig and mini plant. So we have assigned temp1, temp2 for the LM35. Also, we have included the library of one wire and Dallas temperature because we have used a DS18B20 temperature sensor. The temperature one is a DS18B20 temperature 2 and 3 is LM35 and temperature 4 is DS18B20. The next code that we have used is the time and temperature code. This code is used for us to find the temperature for or the temperature after the heat exchanger system with respect to time. The data gathered in this code will be put to Excel in order to make the graph. After the serial monitor on the Arduino has generated the time and temperature values, it will be put to Excel in order for the researchers to make a set point, as you can see in this file. Here we have the set point and the values. This is our primary code. We have gathered all our instrumentation and control system in this one code. We have included the servo motor control, the temperature sensor, and the flow meter. We have included, as you can see, the library of servo, one wire, and Dallas temperature. We have assigned that the flow meter will be put at digital pin 2, the one wire at digital pin 9, and the servo at digital pin 8. The condition is, in this code, that first, it will display the temperatures 1 and 4, the temperature before and after the heat exchanger system. Next, it will display the flow rate of water using the flow sensor. The condition in this code is that if temperature 4 reaches 39 degrees, it will turn off. And it will only turn on if the measured temperature at temperature 4 is 41 degrees. Then the servo will rotate 180 degrees, indicating that it is on.
Today, I will perform one experiment for this audio-visual presentation. In this air compressor test rig and mini plant, there are 4 kinds of temperature sensor, which is all of them is LM35. But we, as researcher and this group, replace 2 LM35 with DS18B20. We replaced them at temperature 1, which is the compressed air that comes out at the compressor, and temperature 4 as compressed air that comes out at the any heat exchanger. We have 2 heat exchanger, heat up air heat exchanger and water heat exchanger, but in this experiment we are just using one, which is water heat exchanger system. I will show you the different type of sensor at different pipe. I will show you the different places where in the temperature sensor is located. Temperature 1, which is DS18B20, that comes out at the compressor, is located here. This is the hottest point or pipe in this test rig. Then temperature 4, which is the compressed air that comes out at the water heat exchanger. This one is our temperature 4, and this is the heat exchanger. We are just using water heat exchanger for this experiment. And then we will be using the program which it reads all for temperature sensor. This code is explained a while ago. Here in the serial monitor, we can see that the normal temperature of the room is 28.5. That is the average. These are the temperatures when the air compressor, test rig and mini plant is turned off. The normal temperature, as you can see, the average is 28.5 degrees Celsius. That is the minimum temperature. To perform the experiment, we will control the temperature when it reaches the peak or the highest temperature. For the review, we will control the temperature at temperature 4. So we will use a program that which the Arduino will read only the control variable, which is temperature 4. Together with the temperature 4, which is the control variable, it will display also the time it was read. As you can see, our set point is 40 degrees. So the program is like this. If the temperature is less than 39 degrees Celsius, the servo will be rotating at 0 degrees. And if the temperature rises up to 41 degrees, the servo will rotate on his 180 degrees. Our set point is 40 degrees. To reach the maximum temperature or the peak of the temperature, I will turn on the test rig and wait for the maximum temperature to come out. I will set the pressure at 2 bars so that the airflow meter will read at 40 liters per minute, assuming that the consumption of this compressor is 40 liters per minute. We will maintain the pressure reading at 2 bars so that the airflow meter will maintain at 40 liters per minute, which is our assumed consumption. You can see temperature 1 is slowly rising up because the test rig is turned on. We will wait for the maximum temperature to be reached. As our past experiment, temperature 1 ranges up to 50 to 55 degrees Celsius, and at our temperature 4, the range is 39 to 45 degrees Celsius. It depends at the weather of the day. While waiting, I will show to you our past experiment, which we are able to create a graph. Using Excel, we input the reading of the Arduino from the serial monitor to the Excel, and then we created the graph. At the graph, you can see our set point is 40 degrees. If the temperature 4, which is our control variable, reaches 41 degrees or equal to 41 degrees, the servo will turn on his 180 degrees, which the AC motor will be turned on. So if it turns on, the air will be cooled, as you can see there. And when the temperature reaches below 39 degrees or equal to 39 degrees, the servo will turn to 0 degrees.
which is the AC motor will stop flowing of water. Then the overlap, as you can see, is reaches up to 38.6. Then the temperature will rise up again, and then the cycle will repeat. When it reaches 41 degrees, the servo will turn 180 degrees, and so on and so forth. This is the overlap of the temperature if the servo is turned off, and this is the overlap of the temperature if the servo is turned on.
After 20 minutes, the temperature at the air compressor test rig reaches its peak or its maximum. As you can see, the reading at the temperature 1 will be 56 degrees Celsius, and at the temperature 4 will be 42.31 degrees Celsius. That temperature should be constant so that we can control later and create a new graph and perform another experiment.
I will use the program which we can create a graph using Excel. This program reads only temperature 4 and the time. As a review, when the temperature reaches below 39 degrees or equal, the servo will be at 0 degrees. The motor will turn off, and 41 degrees or equal above is 180 degrees, which the motor will turn on. I will upload this. And as you can see, the temperature 4 reads 42.7 degrees Celsius. And the servo is at this 180 degrees. Because of that, the motor will start to turn on and the water will start to flow. If the water starts to flow at the water heat exchanger, the temperature at temperature 4 will be going down. As you can see, as the water flows to the water heat exchanger, the temperature goes down. As you can see, the temperature starting to reach 39 degrees, and the servo is still at his 180 degrees, and the water is continuously flowing. We will wait until the temperature reaches 39 degrees or below, so the servo will turn at this 0 degrees. So as you can see, the temperature is slowly getting to 39 degrees. It reaches 39 degrees, so the servo should turn at this 0 degrees. Unfortunately, we don't got it at camera, but we can see that the water flow is turned off and the motor is turned off. Then the reading should start to rise up. The temperature should start to rise up. Even though the pump is turned off, the temperature is still going down. But after how many minutes, the temperature is starting to rise again. We will double check if the water flow is still turned off, and the servo is still at this 0 degrees.
So we will wait until it reaches 41 degrees again, so that the servo will turn to 180 degrees. The temperature is starting to rising up, so that the camera will catch the movement of the servo. We will wait until it reaches 41 degrees. The movement of the servo is nearing. As you can see, the servo turned on because the temperature rises. The servo is at 180 degrees. The water will start to flow. Then again, we will wait until the temperature will go down again. As you can see, the servo is still at 180 degrees and the pump is still flowing. Again, we will wait until it reaches 39 degrees or below. The temperature is slowly going down, so that the camera catch the movement of the servo. We will wait until it reaches 39 or below. You can see the servo turned to its 0 degrees because the temperature reaches 38 degrees Celsius, 38.8. Then the water flow stopped.
Yeah, boy.
And now the experiment is done. We will turn off the air compressor test rig and then check the reading and put it into the Excel and make a graph on it. Using the reading at the serial monitor, we will put it into the notepad and then apply it or put it into the Excel so that we can put the reading at the Excel. You should first copy the reading at the serial monitor to the notepad. Open the notepad file at the Excel. Experiment 2. Gago. The limiters, check comma and finish. Then you will see the reading at the serial monitor at the Excel. Then we will create a graph. In our experiment, we can see the graph. Our set point is 40 degrees. You can see this is the 40 degrees. At the starting point, the pump is turned on, so the temperature is going down. Then when it reaches 39 degrees, the motor will stop, so the flow will stop. But here is the overlap. Then the temperature start to rise up again. When it reaches 41 degrees, the motor will start to flow water. Then the temperature is going down again. Then the cycle will go on and go forth. We are now done at the experiment.
So I will discuss to you the overall heat transfer coefficient of the heat exchanger system. As you can see, the water heat exchanger system is placed like this. Water flows through this direction through that, and air being pumped by the compressor flows through here. The heat exchanger is the primary source of the transfer of heat in the heat exchanger system. As you can see, there are two heat transfer modules on the air compressor test rig and mini plant, which is the air intercooler and the water intercooler. The primary objective of the researchers is to control the flow of water through the water intercooler. In order to compute for the overall heat transfer coefficient in the heat exchanger system, we have to use the formula Qt is equal to U times A times LMTD. Where Qt it's the average heat load on the heat exchanger. A is the area of the heat exchanger. LMTD is the log mean temperature difference. And U is the overall heat transfer coefficient. We'll use this formula to get the overall heat transfer coefficient needed in the system. Now, in order to measure for the overall heat transfer coefficient, first we have to measure the heat load on the water flow rate. So this flow rate is read in the flow sensor using the Arduino. Dito, the values read is liters per minute, which is then converted to meter cube per minute and then converted again to meter cube per second. This is the formula used in order to find the mass flow rate, the density of water, and the measured volume flow rate of water from the cooling tower. This is the mass flow rate computed. Now, the specific heat of water is given by 4.187 kilojoules per kilogram Kelvin. The inlet temperature and the outlet temperature is the measured temperature using the temperature sensors, which is LM35. This is the temperature difference between these two using the formula delta T is equal to T2 minus T1. Reminder that the inlet temperature and the outlet temperature is the temperature inside the heat exchanger system. Now, using the formula MWCP delta T, we can now compute for the heat load on the water. Next step is we measure the volumetric flow rate of air. The measured value of the flow rate of air is 40 liters per minute. We converted it to meter cube per minute, then converted it to meter cube per second, which yields the value of 0.000667 meter cube per second. Now, this value is measured using the airflow meter. Next, the density of air is 1.293 kg per meter cube. Using the formula of mass flow rate, which is MW is equal to V times the density of air. Now we can measure the mass flow rate of air, which yields the value 0.000862. Now, The specific heat of air is 1.005. The inlet temperature is measured at T1 and T4. T1 is located before entering the heat exchanger system. T4 is located after the heat exchanger system. Now, we will use these two values to get the delta T, which yields 12.44 degrees Celsius. Now, in computing for the heat load, we will use this formula: the mass flow rate, the specific heat of air, and the change in temperature between T1 and T4. In computing for that, 0.0 we will yield the value 0.01077777 kilojoules per second. Now, the computed value of the heat load on the air and the water will be QT. QT is the average load on the heat exchanger. We'll use the formula QT, QW, the heat load on the water plus the heat load at the air, and then divide it by 2. Now, in getting for the QT, we have the value of QW, which is 0.948332. The value of QA is 0.01077777, both in kilojoules per second. Now, we will get the average for which we will yield the value of 0.479554 kilojoules per second. So, in order to get the area of the heat exchanger system, we will use the formula pi times the diameter, which is 63 mm or 0.063 meters, multiplied by the length. The given length is 21 cm or 0.21 meters. Now inputting the given values, which is pi times 63 mm times 21 cm, we will get the area of 0.041563 meters squared. So, next step is we will measure for the LMTD. The LMTD stands for log mean temperature difference. The log mean temperature difference is used to measure or determine the driving force of heat transfer through a flow system, most especially in the heat exchanger system. Now, the LMTD is given by the formula T1 minus T4 minus T2 minus T3 over ln of T1 minus T4 over T2 over T3. As you can see, this is the measured temperature in the air compressor test rig and mini plant. These temperatures are measured at various these temperatures are measured at various points using LM35 and DS18B20. Now, in computing for the LMTD, we will input the values given 51.5 minus and we will yield the answer of 11.11213. So bale, we have these values on our computation. Now we will use these values to compute for the overall heat transfer coefficient. Now the objective is to find U. U is the overall heat transfer coefficient. Now using the formula, QT is equal to U times the area times LMTD. Now, we'll cancel out this. Now, we will yield to the formula the average heat load over the area multiplied by the LMTD. Now, we will use these values to compute for U. Now, U is equal to 0.47955 kilojoules per second over 0.041563 meter squared multiplied by 11.11213. And we will yield to the value 1.038319 kilowatts per meter squared Kelvin. Now, this is the overall heat transfer coefficient on the heat exchanger system.